for solution processed organic semiconductor thin films. Okay, and then it's introduction, and then it's the online part. About the reference paper, we use these two reference paper for this report. Okay, about the first one, introduction. Part one is importance of crystal orientation. The orientation of a grain strongly influence electric conductivity, ion diffusion, charge transports, and electrochemical properties. Okay, about the review papers, let charge transport entropy within cross-line domains can vary by orders of magnitude depending on grain orientation and grain boundaries. Therefore, the controlling crystal airline environment is essential for achieving high-performance thin film devices. And in the lithium cobalt oxide thin film study, the authors demonstrated that different substrates include different preferred orientation. And then it's why solution process. A solution process has become an attractive technique for thin film fabrication because it offers several advantages compared with the conventional vacuum-based deposition method. And they can low cost and scalable, large area deposition, and flexible substrate compatibility, and energy efficient manufacturing and roll-to-roll production. Okay, and the next one is fundamentals of thin film crystallization, and they have three different steps. The first one is nucleation. During the solvent evaporation, the concentration of solution gradually increases once substratation is reached and crystal nuclei begin to form. And the next steps is crystal growth. The review paper reported the importance the crystal growth significantly increase the cohesion, length, and carrier mobility in organic semiconductor thin film. And then the final step is the morphology evolution. One important mechanism discussed in the paper is Manning's graded alignment, where directional solution evaporation guided crystal orientation along the preferred direction. And then it's the preferred orientation in thin film. First one, we define a definition of preferred orientation. The review paper enhanced the crystal orientation strongly affects charge transport and devices performance because electrical conduction and ion diffusion are anisotropic in crystalline materials. And they have different types, the remotely oriented and professional oriented. And they have different compression, all peaks of flow, power diffraction, intensity ratios, and specific peaks. And then next is a XRD interpretation of preferred orientation. When grains are randomly oriented, the relative intensity of different peaks follow the standard powder diffraction data. And about the paper, the compress the relative intensity of their three major diffraction peaks is 003, 101, and 104. Okay, and then the next is example of XRD preferred orientation. When grains are randomly oriented, the relative intensity of diffraction peaks follow the standard powered diffraction data. However, if the Thin film contains preferred orientation. Some different peaks become significantly stronger while others are suppressed. And then solution process control strategy. The first one is the solution engineering. Use the review paper explain the solvent properties strongly affect. They use the evaporation rate, subtraction, molecular diffusion, and field flow structure, crystal packings, and domain alignment. And then it's the anti-solvent crystallization. In the anti-solvent crystallization, a second liquid with a poor solubility for the semiconductor is introduced to induce a controlled crystal growth. And the final is Maragoni flow control. This approach improves the film uniformity and out of plane alignment and crystal orientation. Okay, and then about the solution process control strategy, we use the solvent vapor annealing, means SVA. First one is this one, and then substrate effects and adapt and activities. About the first SVA, the grain size increased, and then the second is defects decreases, and then the final is charge mobility improved by 2 orders of magnitude. And then it's the case study about the lithium cobalt oxide thin films. The first one, this paper used the soft solution process system. The process are performed in an autoclave containing the platinum and metal substrate immersed in the procedure solution. This paper explain the different diffraction occurs when crystal explain are panel to the substrate surface, therefore the strong diffraction intensity corresponding to the large population of alignment grains. And then it's a SRD, the pattern of lithium cobalt oxide thin film. The enhanced the diffraction intensity of specific peaks confirmed the formation of strong texture and preferred orientation in films. And then it's about a case study that use the substrate induced orientation. It's one of the most important finding of the paper is the substrate material strongly influences crystal orientation and morphology. The author conclude that the cobalt the substrate and can professional the 003 orientation and another substrate, a professional 101 orientation. And then it's the electrochemical properties. The electrochemical properties performance the lithium cobalt oxide films was evaluated using the voltammetry in the voltage range about the 3.3 to 4 to 4.3. This includes the reversible lithium insertion and extraction in the lithium cobalt oxide substrate. The paper report that the films exhibit the stable cycle behavior, little capability fading occurred. The good electrochemical activity was maintained. And most importantly, the preferred the orientation affect the lithium ion transport and others explain that 003 orientation grains mainly transport lithium through the grains boundaries, and 101 oriented grains all easier lithium diffusion through the grain interiors. Therefore, the 101 oriented film exhibits more favorable ion transport characteristics.
Next, I will discuss the application section. Solution process control is widely used in optoelectronic devices, energy conversion, semiconductor device, and sensor. During thin film deposition, controlling nucleation, crystal growth, and microstructure can significantly improve the crystal orientation of the thin film, thereby optimizing the charge transport or overall performance of the device. The following are the core application area and the components of a solution process control. Perovskite solar cell. This is the most highly anticipated application area for solution process control in the recent years. The quality of the polycrystalline thin film of perovskite materials directly determine the power conversion efficiency. Process control method. Anti-solvent crystallization. Dripping an anti-solvent during the spin coating to induce rapid and uniform localized supersaturation, and additive engineering, such as adding molecular like DNDBS to regulate crystallization connected. Advantage of orientation control, guiding the perovskite crystal to form a strong preferred 100 orientation via anti-solvent, dripping or solvent engineering. The orderly alignment provides a vertical charge transport highway related to the substrate, which dramatically enhances charge mobility, reduces tap state density, and suppresses charge recombination in the grain boundary. This is an ion battery thin film electrode. In microsolid state battery or thin film battery, the crystal orientation of electrode materials has a decisive impact on the interconnection and the interconnection rate of lithium ions. Process control method. Substrate-induced orientation. Example, using a melt solution step process to grow thin film on different metal substrates, such as cobalt or nickel, followed by high temperature annealing. Advantage of orientation control. Lithium iron diffusion in lithium cobalt oxide is highly anisotropic. If the crystalline grain exhibits a 003 orientation, the lithium ion channel run parallel to the substrate, which hinder the vertical entrance and exit of ion. Conversely, controlling the process to exhibit a 101 or 104 orientation align the lithium-ion diffuse channel toward the surface, significantly enhance the charge discharge rate in the electrochemical performance. Metal oxide semiconductor and sensor. Wide bandgap semiconductors, such as zinc oxide, are widely applied in transparent electrode, UV photodetector, and gas sensor due to their high electron mobility, optical transparency, and excellent piezoelectricity and photoconductivity. Process control method. Chemical-based deposition and hydrothermal deposition. Prior to the reaction, a dense zinc oxide seed layer is typically pre-deposited via spin coating to induce the subsequent growth of the vertical, highly oriented narrow rod or thin film in the solution. Advantage of the orientation control. Zinc oxide possesses a wall-side structure. When the thin film exhibits a highly preferred 002 orientation along the Z-axis, the film surface becomes exceptionally smooth and uniform, yielding the most outstanding piezoelectricity and vertical electrical conductivity. Organic semiconductor and thin film transistor. In flexible electronic and wearable devices, the alignment of a small molecular or conjugated polymer organic semiconductor, such as TIPS, pentans, and P3HT, tremendously influence the switching speed of the device. Process control method. Solvent vapor annealing, which use specific solvent vapor to moderately swell the deposit of organic thin film. Increase molecular mobility to rearrange into a more ordered crystalline structure. More or Maragoni flow control to regulate fluid behavior during droplet drying, eliminating or exploiting the conferring effect to achieve larger area uniform mechanical alignment. Advantage of orientation control. The overlapping direction of organic molecular orbital determine the efficiency of charge transport. By controlling the critical alignment of molecule, the staking direction can be aligned with the direction of current flow, thereby boosting the field effect mobility by several orders of magnitude. Outlook and conclusion. Also, the aforementioned applications have achieved immense success at the laboratory scale, such as small area spin coating. Solution process control is currently moving toward the following direction to achieve commercialization. Large-scale, large area coating. Transfer processing technology to a roll-to-roll coating, inkjet printing, or slot die coating, while still maintaining precise control over the critical orientation of the film. In stereo characterization, combining real-time SRD or optical characterization tool to monitor crystallization connected in situ during the thin film deposition and solvent evaporation drying process, enabling automatic process control. Controlling the crystal structure and the preferred orientation of a thin film through solution-based technique is a powerful strategy to enhance their electrical, optical, and mechanical performance. By adjusting key parameters, it is possible to modulate nucleation and crystal growth pathway, allowing research to fine-tune film property at a molecular level for next-generation electronic and energy technologies.